Hello everybody, it's 3 p.m. on the third Thursday of April 2026 and here we are here again for the 3D Thursday webinar. Today is special because today we hit a score. And for those of you who are wondering what I'm saying, score is an old English word for the number 20. So this is our 20th episode. And I extend a very warm welcome to all of you on a very hot summer afternoon. And all of you are very well versed with the topics of 3D printing and how it continues to reshape many industries, right? From aerospace, automotive, healthcare, education, consumer products, everything. And today's topic is also something that is relevant to all these industries that I just mentioned. So the topic for today's webinar is transforming additive manufacturing with simulation intelligence. In this webinar, we'll explore how advanced simulation enables faster, smarter design to manufacturing workflows. We'll also discover how simulation-driven insights help optimize part performance, reduce build failures, and minimize material waste. Now, for anybody who's a practitioner of AM will know that these are essential KPIs, right? So let's learn how to bridge the gap between design, innovation, and production readiness with integrated digital workflows. So join us to see how simulation intelligence is reshaping the future of additive manufacturing. We'd love for you to stay involved throughout the session, and please note we have a surprise for everyone who attends till the end. So make sure you attend till the end. We have a dedicated Q&A session towards the end of the session, but feel free to drop your questions anytime you have them in the chat box. I repeat, in the chat box. We'll do our best to cover as many questions as possible, and we'll group similar ones together. A quick note, today's webinar is being recorded for learning purposes. By participating, you agree to the recording and its distribution within our learning community. Now, it is my pleasure to introduce our speaker for today, Mr. Shripathi V. He's the Global Director, Aerospace and Defense, Business Development at MSC Software, which is a part of Cadence. Mr. Shripathi V is a seasoned professional with over 20 years of experience, and currently he serves as the Global Director, Aerospace and Defense, Business Development at MSC Software, part of Cadence. He brings extensive expertise in simulation-driven engineering across aerospace, defense, and advanced manufacturing domains, though I can definitely say that his favorite domain is aerospace. He actively contributes to industry forums such as ASME and additive manufacturing domain conferences, sharing insights on simulation-led innovation. His work includes solution implementation and thought leadership in design optimization, process simulation, and digital engineering and manufacturing workflows for additive manufacturing. He combines deep industry experience with an applied research perspective to advance simulation-driven product design and manufacturing. He is a member of the SAE India Aerospace Forum and serves on the SAE S19 Committee for Digital Engineering Standards in Aerospace. We're excited to have him share his knowledge and experience with us. A warm welcome to you, Shripathi, and over to you. You're on mute.
Yet again. Okay. Thank you, Akshata, and thank you, Prathidi team. I would like to mention Manoj as well for coordinating this. I'll switch off my camera for a while when I talk because it distracts while presentation goes on. While I would prefer to have dialogue, it would be a monologue for some time, but anybody would like to drop in messages in between and then we can reshape it. I welcome that. I also have Sandeep Manukar on the call, who works with all the organizations on additive and other manufacturing technologies. Any questions comes in, we both will try to do the justice to our best of the knowledge. So with that, uh, yeah, with your permission, Akshata, shall I start the presentation?
Absolutely. We're waiting for it. Shripathi, I think you went on mute again, but
It
we
is
see your.
putting me on mute automatically.
Oh,
So now I think it should be fine. I'll just
okay.
switch off my camera.
Oh,
So, is it visible?
yes.
Great. So I would like to maybe start with a uh, what do you call it as saying. Um, there is always a betterment, or we call it as the best of the best we can always do, and things do evolve over a period of time, and it's endless. Additive manufacturing is such a domain which has been evolving very fast. I think we are all part of it. I've been part of it since about 12 years now, and I see a huge growth and acceptance percentage as well in the industry is much more. So with that, I think we always look at uh, who we are and what we do. I'll just take a couple of minutes of letting know what we are and how do we connect to all the organizations here in the additive world. Firstly, MSc software is almost around 62-year-old plus. We actually were part of NASA. When I say this, MSc Nastran, which was born as a first structural solver across the globe, which is called as NASA Structural Analysis, is born out of NASA in 1963. And the two gentlemen whom you see on the top left, McNeil and Swender, found this. We also are the 10 original software companies in the world, alongside of IBM, Cisco, Microsoft, only simulation company who stands there. And we are proud to be part of almost all the aerospace programs in the world, be it be US based or be it be India based. We are pretty much connected. And of course, there is no end to innovation, and we always will continue to do so. Our work with India, I will be specific to India because we are all here for learning and sharing the knowledge what can really do better for both our country, and we can do something from our country to others. We work on almost all the projects across the DRDOs and I would say other labs, which includes be it be like LCA program or AMCA or SARAS, or even all the DRDO's, weapon programs, we are integrally, we are part of that. So, out of all the, what do you call it as solutions we have, we were famously known as MSc Nastran company because nobody knew anything else what MSc does. Uh, and I would like to highlight that in 2015, you would see here, we acquired a company by name Simufact. So Simufact stands for simulation, of manufacturing, Simufact, and it actually included welding, forming, forging, and also additive manufacturing during that particular period of time. And it focused on metal additive, and I will actually talk about the other additive program or solutions also what we really house, but Simufact really works on the metal additive platform. So I would say from the solution set we have, our idea is to make sure that there is a end-to-end simulation capabilities which can help the customer to really de-invest, or we call it as reduce the investment on physical tests. I think we will take some case studies and also discuss anything which comes in this particular forum. So I would like to start with DFAM. All of us are aware of design for additive manufacturing is something which really exists as a interest for all the AM engineers, or I would say enthusiasts. But there are challenges which comes through. Say, for example, can I really do everything in one go? Optimizing the structure, smoothing the structure, and actually output a CAD file. Can I do that? I'll go through that. And can I really make sure that all the manufacturing constraints are really taken into account? And that is something, or not all, most of them. So that is something which is done in MSc Apex Generative Design. I'll also talk about what you see on the right hand side is basically a drone chassis or fuselage, whatever you can call it as, being fully optimized from scratch. And what we do is it is a single GUI, or you can simulate using generative design approach of MSc Apex will support both metal and polymer based additive manufacturing. So um, I would like to maybe take some examples and then explain you. This is one of the customers case where lightweighting of bottle gripper was supposed to be done. What you see here is a gripper, and this lightweighting is again not really optimum with subtractive manufacturing. And what you see here is the case where uh, we took about, say, 3 minutes for a pre-processing. And if you have a laptop which has GPU, you can solve it in your laptop in 60 minutes. That means the entire optimization cycle itself takes 60 minutes on the laptop. If you really don't have a laptop to solve and you would like to use uh, a server which has about 65 core, 64 core or 128 core, parallel processing, you can use that, and that takes about 20 minutes and 2 minutes for post processing to export the geometry file. And this is something which we have clocked on a real time, software usage time, and you're able to see what we are doing here is uh, specifying the design areas and non-design areas and creating the you know case for optimization. And you can see that it gave a optimized geometry which is compliant for additive manufacturing. And it also gives with the loads what you apply, what is the stress values and the displacements. And thus you can actually control your structural strength of the requirement, whatever you have. So when we say this, the GUI is built to ensure that you are not really having a GUI which is different from a CAD environment. So it's easy to use. So this is something which I wanted to show. So what you saw on the first slide was before optimization, and this is after optimization and the print. So this is another one of my favorites because one of my colleagues worked on this. Uh, I don't know, about 7, 8 years ago, and this is a satellite bracket. And this satellite bracket had a target weight reduction of 40% itself. Means, the target by the organization is to hit 40% reduction, but we could actually hit about 55% with 31% stress reduction and 79% stiffness increase. You know that stress and stiffness are, inversely related, and that is something which is shown here. And we are able to find out a plan of, say, for example, 6 or 7 designs which are feasible, and you can actually look at one of the final designs which can be selected. And the assembly is also done for the satellite. It's a TSAT product. So then going into what is called as end-to-end simulation, what we really spoke about. So first is to do a DFAM. DFAM is going to actually allow you to import a geometry and specify material properties, specify loads, and then say that these are my constraints, your stress, your displacements, or your constraints, and then come out with the geometry. Now, once you are actually out with the geometry, you can do the feasibility study of the print. How many parts can I print? And what is the best orientation to print? All of these things within Simufact Additive for a metal components. And Digimat AM, or we call it as additive manufacturing for polymers, you can do with Digimat AM, transferring the same data. So metal 3D as well as polymer, both are pretty much supported. However, today's discussion would actually be more on metal and less on polymer. And yeah, if you feel it was useful, we can actually have another session on polymer. So now coming to the simulation of additive manufacturing. Why do we have to simulate, first of all? If you are already a company or an individual who owns the machine, it could be a EOS or a SLM or a Renishaw, whatever the machine, you would have seen that there is either a recoater jam or there are shrink lines issues. There could be, a distortion. When I say this, your intended shape would have not been achieved. All of these things are actually a day-to-day problem. And to address this, you need not have to do trial and error. You can simulate. Now, how do you simulate? There are ways to do that. So, firstly, I would like to maybe mention that all that I speak may not be there in the slide. Since the recording is available, maybe that will be useful. So, there are three levels of simulation which we can do, and those three levels are: one is macro, where you don't consider the thermal effects. And when I say thermal effects, no consideration of your layer to layer thermal effects um, uh, in any way. It's purely a approach which is based on the angle of the print and the settings of the machine. So now second part is meso, where you have every layer. This is LPBF I'm talking about. Every layer is being actually coated, and then you have sintering, and the thermomechanical behavior between these two is called as meso, and micro is grain level, and we will go into that particular details in the future slides. So what are the four areas where we can simulate is part printability, where we can actually look at specifying the process parameters like the layers, the laser settings, and even you can actually look at coming out with the cost, which I will show in the later slides. And you can actually look at uh, you know simulating and getting what is the distortion and stress. Manufacturing risks like recoater jam, or part failures, the cracks, support structure failure, and cold and hot spots, all of these things are possible. And you can also do process optimization, where what is the best build orientation. One, to save the material. For example, if I can save the support structure material, or with a proper build orientation, how many parts can I build? Something like nesting, right? So how many parts can I build in a particular given volume? And also, if you already have a structure where you can mitigate the distortion by compensating the geometry, we will be able to do that automatically. And post build operations, for example, if you want to separate out from the base plate the printed part, what happens to the structure. And we also kind of somebody use magics. You have to take the data inside directly. We can support that, and we integrate the job preparation for either SLM, EOS, or Renishaw, or any other machines. So what we see here is basically this particular beam. I think everybody would know. It's a standard beam which is being, or we call it as coupon, which is printed for calibrating a machine. And pre-calibrated machines are already available, and if you want to calibrate your own machine, you can always do that. And what you see here is the pre-compensation of the geometry, and this is for an aerospace bracket. And and I am sure Akshata would know it. We printed this long ago in Wipro 3D. So now, when you look at MSC Software's way of polymer printing, we have FDM, SLS, CFF, all of these solutions. I will not go into the details of polymer, but yeah, pretty much the same what do you call it as features do apply for polymer. When I say this, polymer goes into a little more deeper of materials where metal is not. Just to take a LPBF case, almost 80% of the failures one can actually simulate, and 20% is inevitable because of certain cases which are not really part of the simulation. So be it be recoater crash or shrink line issue or overheating, that is overheating by conduction, convection, and also radiation. We can look at it. And conduction, convection plays a major role. And say, for example, if your support failure or cracking is something which is very, entry level analysis which can be done. And the standard material databases do exist, be it be TI-64 or Inconel or steel or any of these particular material properties already exists. Now let us go into the cost estimation for R&D engineers. One is you have failure or say for example simulation itself is an R&D for us. But for the production houses, the cost makes a major impact. So how do you really look at cost estimation? So I'll just go get into some of the examples. Say for example, the one you see on the left hand side is the light hinge, and there is light hinge plus, and I'll talk about it. So there are different subcategories which actually contribute to the cost. So which I will actually talk about. So say for example, what is machine hour rate, what is the material cost, and then the build costs, basically including the material costs. These are all actually uh, calculated based on the inputs you provide. For example, you provide the powder cost, and as well as any of the say for example data, like what is your machine running cost per hour, which is the power consumption and all these things, and you can actually come out with an estimation report. So this is one of the cases for aerospace brackets. It's a butterfly bracket, everybody would know it. It is aluminum alloy, and unit price for this usually without simulation or without doing a cost optimization was quoted by one of the organizations is about 85,000 plus. And what is being done is basically look at optimizing the support structure and as well as optimizing the operation time. When I say this, you can look at really optimizing the print time as well, based on the proper orientation for the structure. And what you see on the right hand side is to uh, have a cost for single build, and then you can also do nesting if you have, say for example, a machine which can build multiple parts, and those particular simulation also possible. And with the optimized cost, you can see that it comes down to 65,466. With further optimization, it's about 44,800. Of course, 44,800 is more squeezed. Maybe what would be realistic is to consider about 66,000. So what we are talking is a good 20% plus saving for a simulation based approach. Now let us get into a little more advanced part of it. So Raytheon Technologies has one of the divisions which works on additive manufacturing, which maybe most of you know. Um, when these particular cases come to us, it is a joint approach, and we do a R&D required at our end as well, and then we develop some of the solutions if they are missing. So in this case, the failure modes, or we call it as simulation requirements, were different. So something like the effects of say for example keyhole formation or balling or surface roughness, lack of fusion, all of these things are something which is of the concern. And you can see here that the data of each material, the PV diagram or the data coming from this particular PV diagram is already part of SimuFact. And we actually have we usually had other solutions also. When I say this, we had our own scanner when we were part of Hexagon, but that is not anymore a solution. So because we are part of Cadence now, but any other scanner you have, you can still take the data and then process it. So this PV diagram based data provides the predictions for mesoscale. When I say this, you can see the plots of the I'll go to the next slide. You can see here that these are the color plots where if you are having green, it is a stable keyhole, unstable keyhole, which is saffron in color, and then you have fully green, which is defect free, and unmelt is again orangish. So you actually have this particular color plots on your structure. This is again, as I said, purely a simulation approach, and you can look at optimizing it further based on optimization techniques, which I'll talk about in the future. So parameter inputs are pretty much simple. You can see here that the power, speed, spot size, these are the common parameters which we have to have. The standard machine properties are existing already, and you can actually look at setting whatever the values you are giving to the machine, the same settings are to be there in the simulation for you to achieve whatever you want. This can be worked back. When I say this, optimized parameters can also be something which we can look at in the optimization. So materials which are existing in the database includes TI64, Inconel, and steel and aluminum. And material also can be added. When I say this, material properties can be added with the data like dynamic viscosity, surface tension, laser absorptivity, and others. And all of these things are something which enables even, say, for example, somebody studying the materials own optimization for a particular application can be done. So this is Inconel 718, and then you can see that the build, happens. This is meso. That means every layer you will be able to see what is the, uh, output. I will just go and show the final output here. So there's next slide which shows, you can see here the simulated data is on the left-hand side, and the simulated data is superimposed on the actual printed part. And the visual effect can be seen in terms of all that what we are trying to look at. So similarly for this aerospace bracket, we have done the stuff, and yeah, it gives you the similar plots. So I would like to go into the case studies, and yeah, more interest would be on Q&A. This is Light Hinge Plus, and you can also Google it. The weight saving has been more than 70%, and it was originally weighing about 3.3 kgs and knocked down to almost 1 kg and below. And it also is one of the very well proven structure for a high strength application. And this is something which is already in use for some of the cars. And it's ultra lightweight, and then you have some of the assembly level modelings which are done. You can see here the simulation were done, and as well as the actual part testings were done, and you are able to see that on the printed part. And the same is simulated in our tool like Adams, or Adams plus Nastran, that is for kinematics and as well as the structures. So what you really simulate with the strength and the properties can be taken further for your fatigue, depending on SN curve availability. We can do that, and as well as say for example your dynamic strength, or ultimate strength kind of an analysis. So this was the whole process which was followed. Design space model started from a very basic geometry, and then topology optimization was done. Active bonnet function means, how does it connect to the bonnet, and what is the mechanism used. And then support structure optimization, and you can see here that the testing was done, which you saw the video. And you can also see that most of the parts which are being printed are in I would say bulk, and that again the optimization is done for the parts to be printed in bulk in a particular given machine. So I'll just move forward. So this is another case of green team, and optimization was done for one of the components which I would say undergoes a very high speed rotor dynamics load. And this again is um proven with both optimization and actual experimentation for the loads check. And we are able to reduce the weight in a very, what do you call it as optimal manner. So if you look at the designs, what we have and the process we have followed, already you are aware of DFAM. The DFAM actually gave a shape which has to be for this particular component with 30 to 40% of weight saving. And then we actually checked its stability with um, a tool like Adams, where it does the loads analysis on it and the strength analysis. Once that is done, Simofact is used to really see the printability and as well as any printing challenges or manufacturing challenges. And even the build simulation is done to see any warpages issues. And this is the further simulation which gives its property with the assembly analysis. And once all the simulation are done, it is actually being produced and fit onto the car. And of course, everybody knows the green teams, participation in the races, and you have optimized build. And if you look at the parts, one is why green a team really has to go for this is every gram saved in a racing car is something which is $1 million. And not just this particular calculation what we see here for investing onto the parts print, but every gram for them is always a velocity achieved on the road. And that's what we have done, and that is kind of much more priceless than calculating these particular prices. So even in the healthcare industry, thanks to one of our colleagues who has done this job earlier. So this is a hip joint, and the hip joint had to be really designed and printed. So again, scan was done for the hip joint part. So there is a hip joint which is existing uh, in a good condition, and the scan was done for that. And the one which has to be replaced has to be mirrored, and that was done. And then once the scan data comes in, you have a geometry being built using Apex generative design, and then you optimize the whole thing in the generative design and simulate for this for its build quality and print as particular uh, you know um, sizes are. When I say this, it's a custom made component, and this is done with generative design where we look at optimizing the part. Digimat, because this is not a metal component, this is a polymer component, and that is used for additive manufacturing. And some part which was metal was with Simofact, and Mark was used to test its strength in all conditions. When I say this, in all temperature and loading conditions. So this is the part, and one of the patients who was not from India, and of course the replacement happened at this particular point, and there is a implant which is being inserted there. And you can see that one is there is no chance of any high level optimization, but it has to really be a perfect fitting part. So this is a last slide I wanted to present, because we are talking about aerospace cases. If you Google it, you'll be able to find the weight reduction of Airbus A330 fuel separator. So 75% weight reduction was achieved with both Simofact and SLM, working together on this. And again, additive manufacturing involves, as I said, DFAM to, conformal printing or end to end, and that was done. And I would say, being a part of the digital engineering community, where it's very tough to get the certification. This is not fully certified yet, but it's a great job really to look at how simulation plus manufacturing intelligence, or we call it as even the machine, do play a role in terms of getting the whole process optimized. So with that, I would thank Sandeep